Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question so vast that it almost feels too big to hold in the mind. How big is the universe compared to our galaxy? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the scale of the cosmos together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly, unfolding the story. Tonight, we're not launching rockets or racing across star systems. We're simply widening our view. We will begin at home in a quiet spiral of stars called the Milky Way. From there, we will slowly step outward, past neighbouring galaxies, through immense clusters and delicate cosmic filaments, and eventually toward the vast edge of what we can see. Along the way, we'll discover that distance in space is also distance in time, that the universe is larger than its own age might suggest, and that our position is neither central nor insignificant. There is no rush here. We will move the way starlight moves, patiently, steadily, across unimaginable distances. So take a slow breath. Feel the weight of gravity beneath you. Notice how your body rests against the surface below. Even that gentle pressure is part of a much larger story, one that stretches far beyond our planet. And with that, let us begin at a place both familiar and immense. If you step outside on a clear night and look up, you might see a faint milky band stretching across the sky. For most of human history, that glowing river of light was a mystery. It looked like a cloud, a smear, a soft brush stroke across the dark. We now know that faint glow is not a cloud at all. It is home. That pale ribbon is the combined light of billions of distant stars, gathered together in a vast spiral system we call the Milky Way, our galaxy. To understand how big the universe is compared to our galaxy, we first have to understand how large our galaxy truly is, and that means beginning somewhere very small. Let's begin with the solar system. Imagine the sun, a steady golden presence at the centre of our local neighbourhood. Around it drift the planets: Mercury, Venus, Earth, Mars, the gas giants farther out, each following its quiet path. If the sun were the size of a large orange sitting on a table, Earth would be a tiny grain of sand a few meters away. The outer planets would be scattered far across the room. Already the distances are humbling, but this entire planetary family, the Sun, Earth and every comet and asteroid, occupies only a tiny speck within the Milky Way. Our solar system sits about 27,000 light-years from the centre of the galaxy. A light-year, by the way, is not a measure of time, it is a measure of distance. It is the distance light travels in 1 year, and light moves very quickly, about 300,000 kilometres every second. In a single second, light could circle the Earth more than 7 times. In 1 year, it travels nearly 10 trillion kilometres. When we say 27,000 light-years, we mean that the light from the centre of our galaxy takes 27,000 years to reach us. And yet, even that distance does not place us near the edge. The Milky Way stretches roughly 100,000 light-years from one side to the other. Some measurements suggest it may be closer to 120,000 light-years across. Either way, if you could travel at the speed of light, which, according to everything we understand about physics, nothing with mass can actually do, it would take you 100,000 years just to cross our galaxy from edge to edge. The solar system is not near the centre. It is not near the outermost boundary either. We are located in a gentle spiral arm, sometimes called the Orion Arm, a minor branch between larger sweeping arms of stars. If the Milky Way were a vast city of light seen from above, we would live in a quiet suburban neighbourhood, far from the bright downtown core, and this city is enormous. Astronomers estimate that the Milky Way contains somewhere between 100 billion and 400 billion stars. It is difficult to hold a number like that in the mind. Even the lower estimate, 100 billion, is more than 10 times the number of people who have ever lived on Earth, and stars are only part of the story. Beyond the bright spiral arms lies something invisible yet profoundly important. Surrounding the Milky Way is a vast halo of dark matter, an unseen form of matter that does not shine or reflect light, but whose gravity holds the galaxy together. You can imagine it as an invisible scaffolding, extending far beyond the visible stars, quietly shaping the galaxy's structure. Without this hidden mass, the outer stars would drift away into the night. Now consider something even slower and more patient. Our solar system does not simply sit in place. It orbits the centre of the Milky Way. One full orbit, a journey all the way around the galactic centre, takes roughly 230 million years. That means the last time our planet was in this exact position in its orbit around the galaxy, dinosaurs had not yet appeared. Entire chapters of Earth's history unfold in the time it takes us to circle once. You're not just orbiting the Sun, you're orbiting the galaxy, right now, at this very moment. As you rest and breathe, the Earth spins on its axis. It circles the Sun. And together with the Sun, it moves in a vast, silent arc around the Milky Way's centre. This is the scale of just one galaxy, 100,000 light-years wide, hundreds of billions of stars, a dark halo stretching even farther, a slow galactic year lasting hundreds of millions of Earth years. And yet, as immense as this sounds, our galaxy is only the beginning of the story. When we look at the Milky Way from inside it, we see only a band of light. But if we could somehow travel far above it, far enough to see it whole, it would not look like a cloud at all. It would look like a spiral. Imagine a vast whirlpool made not of water but of stars, a slow, luminous swirl with long arms curving outward from a brighter central region. These arms are not solid structures. They are regions where stars gather more densely, like soft ripples moving through a sea of light. Milky Way is what astronomers call a barred spiral galaxy. At its centre lies a thick, bright bulge of stars. Through that bulge runs a bar-shaped structure, a long, dense region of stars stretching across the core. From the ends of that bar, the spiral arms unwind, curving outward in sweeping arcs. If you were to see it from above, it might resemble a pinwheel turning slowly in the dark. That central region is not empty or quiet. At the very heart of our galaxy lies a supermassive black hole known as Sagittarius, a star. It contains the mass of roughly 4 million suns, compressed into a region far smaller than our solar system. Yet even this immense object does not dominate the entire galaxy. It simply anchors the centre, quietly shaping the motion of nearby stars. And those stars, hundreds of billions of them, are spread across a disk that is astonishingly thin compared to its width. The Milky Way is about 100,000 light-years across from side to side, but its disk is only about 1,000 light-years thick in most places. If the galaxy were scaled down so that it was the size of a large dinner plate, its thickness would be no more than a sheet of paper. It is wide and flat, vast and delicate at the same time. Beyond that thin disk lies something even more mysterious. Surrounding the galaxy is a halo, a spherical region extending far beyond the visible spiral arms. Within this halo drift ancient stars, globular clusters, and most importantly, enormous amounts of dark matter. Dark matter is one of the strangest discoveries in modern astronomy. It does not glow, it does not reflect light, it cannot be seen directly by any telescope, and yet we know it must be there because of how stars move. When astronomers measure how quickly stars orbit the centre of the Milky Way, they find something unexpected. Stars far from the centre move faster than they should if only visible matter were present. According to the laws of gravity, the outer stars should slow down as they move farther from the dense core, but they do not. It is as if there is extra mass, hidden mass, spread throughout and beyond the galaxy, holding everything together. Rather than overwhelming the mind with equations, we can picture it this way. Imagine children on a merry-go-round. If the platform were light and fragile, spinning too quickly would cause it to fly apart. The only way for the outer edges to spin steadily is if the structure is heavier and more solid than it appears. Dark matter acts like that hidden weight. It provides the invisible stability that prevents the galaxy from unravelling. And this hidden halo extends far beyond the visible stars, possibly 2 or 3 times farther than the bright disk itself. So when we say the Milky Way is 100,000 light-years across, we're speaking only of the luminous part. The true gravitational reach of our galaxy stretches much farther into space. Even so, it remains only one galaxy among many. Before we drift outward to compare it with others, it is worth pausing here and letting this scale settle in. You're resting on a planet that orbits a star. That star is one among hundreds of billions. Those stars are arranged in a vast spiral disk so wide that light would need 100,000 years to cross it. And that entire structure is wrapped in an invisible halo of matter that outweighs all the stars combined. If the Milky Way were a continent, our solar system would be smaller than a single grain of sand on one of its beaches. Yet from here, from this grain of sand, we have learned to measure the continent itself. There is something quietly remarkable about that. And as immense as our galaxy feels right now, it is not the largest spiral in the cosmos. It is not the densest. It is not the brightest. It is in many ways an ordinary spiral galaxy, graceful, balanced, and unexceptional among its peers. That ordinariness will matter as we continue to widen our view. For now simply imagine the Milky Way turning slowly, like a silent clock whose hands move once every 230 million years. Imagine its spiral arms glowing faintly in the dark, billions of suns tracing gentle curves through space. And remember that this immense structure, this 100,000 light-year wide whirlpool of stars, is only our local neighbourhood in a universe far larger than it first appears. For most of human history, it felt natural to assume we were at the centre of things. The sun seemed to rise for us. The stars appeared to circle overhead as if we were the still point around which everything turned. The earth felt solid and unmoving beneath our feet, and so it seemed reasonable to imagine that all of creation revolved around it. But the story of astronomy is, in many ways, a story of stepping away from the centre. First, we learned that Earth is not the centre of the solar system. It orbits the Sun, along with the other planets. That realization alone reshaped humanity's understanding of its place in the cosmos. Then, centuries later, we discovered something even more humbling. The Sun itself is not at the centre of the galaxy. It is not even particularly close. Our solar system lies about 27,000 light-years from the Milky Way's centre, drifting along a quiet spiral arm. If the galaxy were imagined as a vast circular garden, we would not be standing by the fountain in the middle. We would be walking along one of the outer paths far from the brightest gathering of stars. And even that is not the end of the shift. The Milky Way is not the centre of the local group, the small collection of galaxies to which it belongs. It shares that space with Andromeda and dozens of smaller companions. The gravitational dance among them does not revolve around us. It unfolds according to mass and motion, not preference. Each step outward has gently removed us from the middle of the picture, but here is something subtle and beautiful. This removal from the centre does not mean we are unimportant. It simply means the universe does not arrange itself around our perspective. In fact, modern cosmology suggests something even more intriguing. On the larger scales, there may be no centre at all. When astronomers observe distant galaxies, they notice something remarkable. Almost all galaxies appear to be moving away from us. The farther away a galaxy is, the faster it seems to recede. This observation is part of what led to the understanding that the universe is expanding. At first glance, this might sound like we're somehow at the middle of an explosion, with everything flying outward from our location. But that is not what is happening. To understand this more gently, imagine the surface of a balloon. Draw small dots on its surface to represent galaxies. Now begin to inflate the balloon. As it expands, every dot moves away from every other dot. From the perspective of any single dot, it appears that all the others are drifting outward. But no dot sits at the centre of the expansion. The centre is not on the surface at all. The expansion happens everywhere at once. In this analogy, the surface of the balloon represents the fabric of space itself. The galaxies are not flying through empty space away from a single point. Instead, the space between them is stretching. Every location experiences the expansion. This means that no galaxy, not even ours, holds a privileged position. If observers in a distant galaxy were measuring the universe, they too would see other galaxies receding from them in all directions. From their perspective, they might also feel central. And yet none of them are. This principle is sometimes called the cosmological principle, though we do not need the formal term to understand its quiet implication. The universe, on large scales, appears roughly the same in every direction. It does not favour one vantage point over another. There is something deeply calming about this idea. We're not at the centre of the solar system. We're not at the centre of the galaxy. We're not at the centre of the universe. And yet, wherever we stand becomes our centre of observation. From here, from this quiet planet orbiting a quiet star, we can measure distances of millions and billions of light years. We can map the spiral arms of our galaxy. We can detect the faint glow of galaxies so distant that their light began its journey before Earth formed. We can even infer the presence of invisible dark matter from the motion of stars. Not being at the centre has not limited our ability to understand. If anything, it has expanded it. Consider again that slow galactic orbit we described earlier. It takes roughly 230 million years for the Sun to circle once around the Milky Way centre. During that long journey, continents shift, species evolve, mountains rise and erode. From the galaxy's perspective, Earth's entire biological history is just a fraction of a single rotation, and yet here we are, aware of that motion. There is a quiet irony in this. The universe does not revolve around us, but we are capable of tracing its revolutions. We are small in position, but expansive in perception. As we continue outward, we will encounter galaxies larger than our own, clusters more massive than the local group, and structures so vast they stretch hundreds of millions of light years across. With each widening circle, the idea of a single centre becomes less meaningful. The cosmos is not arranged like a stage with a spotlight fixed on one location. It is more like a vast field, extending in all directions, where every point can serve as a place of observation. And so, as you rest there now, not at the centre of anything cosmic, you are still at the centre of your own awareness. From this small corner of the Milky Way, on a planet orbiting an ordinary star, In a galaxy that is not especially large or small, you are part of a universe that does not require a center to be magnificent. And this gentle shift away from cosmic centrality prepares us for something even larger, the realization that our entire galaxy is just one among countless others scattered across a structure far grander than we once imagined. If the Milky Way is our vast city of stars, then Andromeda is the neighbouring metropolis glowing softly in the distance. On very dark nights, far from city lights, Andromeda can be seen with the naked eye. It appears as a faint smudge in the constellation that shares its name. To the eye, it is subtle, easy to miss. But that dim patch of light is not a nearby cloud or a single star. It is an entire galaxy, and it is enormous. The Andromeda galaxy lies about 2.5 million light-years away from us. That means the light entering your eyes, if you were looking at it tonight, began its journey before early humans walked the Earth. 2.5 million years ago, our distant ancestors were just beginning to shape the earlier stone tools, and during all that time, the light from Andromeda has been crossing the darkness toward us. Distance in space is distance in time. In size, Andromeda is slightly larger than the Milky Way. Estimates suggest it stretches perhaps 200,000 light-years across from one side to the other, though measurements continue to improve as telescopes grow more precise. It likely contains 1 trillion stars, possibly 2 or 3 times as many as our galaxy. If the Milky Way is a grand spiral of light, Andromeda is a grander one still, and yet, despite its scale, it does not dominate us. It does not outshine our own galaxy from within. From here, it is a faint whisper in the sky. There is something quietly humbling about that. Entire galaxies can appear as small smudges when seen from far enough away. But Andromeda is not drifting quietly in place. It is moving. Astronomers have measured the motion of Andromeda using a phenomenon known as the Doppler effect. When an object emitting light moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts toward red. This subtle change allows scientists to determine whether galaxies are approaching or receding. In the case of Andromeda, the shift tells us something surprising. It is moving toward us. Not quickly by human standards, but steadily on cosmic timescales. The approach speed is roughly 110 kilometers per second. That might sound fast, but in galactic terms, it is a patient drift. Over billions of years, that slow motion adds up. In approximately 4 billion years, the Milky Way and Andromeda will begin to interact gravitationally. Their spiral arms will stretch and distort. Stars will shift their paths. The two galaxies will not collide like solid objects crashing together. Stars are separated by vast distances, so direct star-to-star impacts are unlikely. Instead, the galaxies will pass through each other like misty spirals interweaving, pulled and reshaped by gravity. Eventually, after several passes, they will merge into a single larger galaxy, perhaps an enormous elliptical system formed from 2 once spiral giants. By that time, the Sun will be much older. Earth's surface may be unrecognizable. Humanity, if it still exists in some form, will witness a sky transformed. Andromeda will grow larger and brighter over millions of years, eventually filling much of the night. But that is far beyond our present horizon. For now, Andromeda serves as a mirror. It shows us that the Milky Way is not uniquely vast, not uniquely structured, not uniquely positioned. Spiral galaxies like ours are common. They vary in size and brightness, but the Milky Way is comfortably average, neither the largest nor the smallest. Beyond Andromeda lie countless other galaxies. Some are tiny dwarf galaxies, containing only a few million stars, mere villages compared to our galactic city. Others are colossal elliptical galaxies containing trillions of stars, stretching across distances that dwarf even Andromeda. There are galaxies so massive that they dominate entire clusters, shining as bright, swollen hubs surrounded by swarms of smaller companions. Compared to those giants, the Milky Way is respectable, but not extraordinary. And that ordinariness is important, because if our galaxy were exceptionally large or uniquely placed, it might suggest a special cosmic arrangement. Instead, what we see is a pattern. Galaxies come in many sizes, many shapes, many histories. Spiral arms, elliptical glows, irregular clusters, all scattered across the universe like variations on a theme. Andromeda reminds us that we are part of a broader population. If the Milky Way were the only galaxy, its scale would feel absolute. But beside Andromeda, it becomes relative. Large, yes, but not unmatched. As we widen our view further, this relativity will grow even stronger. We will discover that galaxies gather together in communities, bound by gravity into groups and clusters. The Milky Way and Andromeda are not isolated islands. They are members of a small gathering in a much larger cosmic landscape. For now, imagine standing on a shoreline at night. Across a vast dark ocean, you see another city glowing faintly in the distance. It is not touching yours. It does not overlap. But over ages so long they blur into abstraction, the two cities will slowly drift toward each other. That is our relationship with Andromeda. Two spirals of light, separated by millions of light years, moving together through a universe that is far larger still. When we look beyond the Milky Way and Andromeda, something quietly astonishing becomes clear. Galaxies are not all the same. They are not uniform cities stamped from a single blueprint. They vary in size, shape, brightness, and history. Some are graceful spirals like ours with sweeping arms that curl like slow-moving waves. Others are round and swollen, like luminous spheres suspended in the dark. Still others are scattered and irregular, appearing almost unfinished. The universe is not a gallery of identical forms. It is more like a forest, where every tree has grown in its own way. Let us begin with the giants. In the hearts of some massive galaxy clusters lie enormous elliptical galaxies. These systems are vast rounded collections of stars, often containing trillions of them. If the Milky Way were a large metropolitan area, these galaxies would be sprawling continents of light. Unlike spirals, elliptical galaxies do not display long, elegant arms. They appear smooth and diffuse, with stars orbiting in many different directions rather than along neat circular paths. They are often older systems, having formed through repeated mergers, spirals colliding and blending over billions of years until their structure becomes more spherical and less defined. Some of these giants stretch across distances that rival or exceed 200,000 light years. They shine with the combined glow of trillions of suns. Their gravitational pull shapes entire clusters of surrounding galaxies. Compared to such giants, the Milky Way is substantial, but not extraordinary. And yet, just as there are giants, there are dwarfs. Dwarf galaxies are small systems containing perhaps a few million or a few billion stars. That might still sound immense. Millions of stars is no small number. But compared to the hundreds of billions in the Milky Way, these dwarfs are modest communities. Some dwarf galaxies orbit larger galaxies the way small towns cluster around major cities. In fact, several dwarf galaxies orbit the Milky Way itself. The Large Magellanic Cloud and the Small Magellanic Cloud are two visible examples in the southern sky. They appear as faint cloudy patches, companion systems gravitationally bound to our own. These dwarf galaxies are not merely decorations. They are part of the Milky Way's extended family, slowly interacting with it over cosmic time. Streams of stars from smaller galaxies can be stretched and absorbed into larger ones, leaving faint trails like ghostly ribbons in the galactic halo. between the giants and the dwarfs lie countless intermediate systems, spiral galaxies of varying sizes, lenticular galaxies that sit somewhere between spiral and elliptical forms, irregular galaxies that appear chaotic, shaped by gravitational encounters or bursts of star formation. The diversity is vast, but this diversity reveals something essential. The Milky Way is not uniquely large, it is not uniquely small, it is not uniquely structured, it is a fairly typical spiral galaxy, comfortable in the middle of the galactic size spectrum. This ordinariness carries quiet meaning. If our galaxy were the largest in existence, it might suggest we live in a special location. If it were the smallest, it might suggest we inhabit an unusual corner. Instead, we find ourselves in something balanced, a galaxy large enough to host billions of stars, yet not dominant in the cosmic census. And this balance extends beyond size. Galaxies also differ in colour and age. Some are blue and bright, filled with young hot stars forming in dense clouds of gas. Others are redder and calmer, populated mostly by older stars that have long since exhausted their youthful brilliance. The Milky Way contains both old and young stars. Regions like the spiral arms glow with active star formation, while the central bulge contains ancient stars that have burned for billions of years. It is neither extremely youthful nor entirely aged. If galaxies were living organisms, some would be energetic and vibrant, others ancient and quiet. The Milky Way would be somewhere in the middle, steady, mature, still capable of forming new stars, yet carrying a deep history in its core. And this pattern repeats across the observable universe. Billions, perhaps trillions, of galaxies, each with its own structure, its own rhythm, its own gravitational choreography. As we compare these systems, something subtle shifts in perspective. The Milky Way, once vast beyond imagination, now becomes one example among many, still immense, still breathtaking, but no longer singular. And this is only the beginning of the widening view. Because galaxies rarely exist alone. They gather, they cluster, they assemble into communities bound by gravity. Just as stars gather into galaxies, galaxies gather into larger structures, and as we step outward from individual galaxies, we begin to see the next layer of cosmic organization, a layer that makes even giants seem small. For now, allow this diversity to settle in your thoughts. Imagine a night sky filled not with isolated points of light, but with entire cities of stars, each different in size and shape, some vast and round, some slender and spiraled, some scattered like luminous confetti. Among them, the Milky Way shines, quietly, neither the largest nor the smallest, neither the brightest nor the faintest, ordinary, and in that ordinariness, profoundly connected to the wider universe. When we look at the Milky Way and Andromeda, it is tempting to imagine them as isolated islands drifting alone in a vast ocean of darkness. But they are not alone. They belong to a small gathering of galaxies known as the local group. The local group is not a tightly packed swarm. It is more like a quiet archipelago of islands, separated by immense stretches of space, yet connected by gravity. More than 50 galaxies are part of this group, though the exact number changes slightly as new faint dwarf galaxies are discovered. Most of these members are small dwarf galaxies, modest systems containing millions or billions of stars. The two largest galaxies in the local group are the Milky Way and Andromeda. A third, somewhat smaller spiral galaxy known as the Triangulum Galaxy also plays a significant role. If the local group were imagined as a village of galaxies, the Milky Way and Andromeda would be the two largest houses facing one another across a wide valley. The distance between the Milky Way and Andromeda About 2.5 million light years might sound enormous, and it is, but within the context of the wider universe, it is a close neighbour. What binds this group together is gravity. Gravity acts quietly across space, pulling masses toward one another. Though the galaxies are separated by millions of light years, their combined mass creates a gravitational embrace that keeps them from drifting apart entirely. Unlike the more distant galaxies that are carried away by the expansion of space, the members of the local group are gravitationally bound. Their mutual attraction is strong enough to resist the stretching of space on these smaller scales. Rather than presenting this in mathematical form, it helps to imagine a group of leaves floating on a gently expanding pond. Most leaves drift apart as the water stretches, but if a few leaves are close enough together and lightly connected by threads, they remain clustered even as the surface widens around them. The local group is like that cluster of connected leaves. Within it, galaxies orbit one another slowly. The Milky Way and Andromeda are gradually moving toward each other, as we explored earlier. Smaller dwarf galaxies orbit these larger spirals, tracing long, gentle arcs through space. Some dwarfs may eventually be absorbed, their stars pulled into the larger galaxy's halo. Over billions of years, the structure of the local group will change, galaxies will merge, shapes will evolve. But the group itself remains a coherent system, bound by gravity. Now consider the scale of this group. From one side of the local group to the other spans roughly 10 million light years. That means if you could travel at the speed of light, which, again, is the fastest speed allowed by the laws of physics, it would take 10 million years to cross the entire group. Compared to the Milky Way's 100,000 light-year width, the local group is 100 times larger in diameter. Already the scale is expanding in layers, solar system within the Milky Way within the local group. And yet, even this group is not unique. Across the universe, galaxies gather into similar small associations. Some groups are larger, some are smaller, but the pattern repeats. Galaxies rarely exist in isolation. Gravity encourages companionship. This companionship also affects how galaxies evolve. When galaxies pass near one another, their gravitational fields tug at each other's stars and gas clouds. Spiral arms can be distorted. Gas can compress, triggering bursts of star formation. Over immense spans of time, these interactions reshape entire galaxies. Our Milky Way shows subtle signs of past interactions. Streams of stars in its outer halo suggest that smaller galaxies were drawn in and stretched apart long ago. The local group is not static. It is dynamic, slowly transforming. There is something strangely comforting in this idea. Even on the scale of millions of light years, structures form. Communities exist. Motion is coordinated. The universe is not a random scattering of disconnected objects. It has patterns that repeat across scale. But as large as the local group feels now, it is still only a small region in a much larger cosmic environment. If the Milky Way is a city, and the local group is a village of cities, then beyond it lies an even grander organization. A vast network of galaxy groups gathered into immense superclusters. The widening continues. For now, imagine drifting far above the local group, seeing the Milky Way and Andromeda as luminous spirals facing one another, surrounded by dozens of smaller companions. Imagine their slow gravitational dance unfolding over billions of years. This cluster of galaxies may feel enormous, stretching across 10 million light years, but it's still only a small thread in the greater tapestry of the cosmos, and that tapestry extends far beyond what our ancestors once believed possible. If the Milky Way is a city, and the local group is a small village of cities, then the Virgo supercluster is something far grander. It is not simply a larger group, It is a gathering of many groups. The local group, with its more than 50 galaxies, is just one small member of a much larger structure. Surrounding us are countless other galaxy groups, each with their own spirals and ellipticals, their own slow gravitational dances. Together, these groups form a sprawling supercluster known as the Virgo supercluster. The name comes from the Virgo cluster, a particularly massive cluster of galaxies located in the direction of the constellation Virgo. That cluster acts as one of the dense hubs within the supercluster. Around it are many smaller groups, including ours, arranged in a complex web of gravitational relationships. The Virgo supercluster stretches across roughly 100 million light-years. That number is difficult to hold in the mind, so let us soften it. If the Milky Way were the size of a coin resting on a table, the local group might be the size of a small plate. The Virgo supercluster would be more like a varsity block, encompassing many such plates spread across a wide expanse. From edge to edge, light would take about 100 million years to cross this structure. That means if a flash of light began at one side, it would not reach the other until long after entire species had evolved and vanished on Earth. And yet, even at this scale, gravity still plays its quiet role. Galaxy groups within the Virgo supercluster are drawn toward regions of higher mass. Clusters like the Virgo cluster itself act as gravitational anchors, shaping the motion of surrounding galaxies. Over billions of years, galaxies drift slowly along, invisible pathways carved by mass. Unlike the local group, which is tightly bound and moving toward eventual merger, the Virgo supercluster is more loosely connected. It is a region of higher density within the broader universe, but not all of its parts are gravitationally locked together in the same way. Here, it helps to imagine a landscape of hills and valleys. In the local group, we're within a small valley where gravity holds us firmly together. In the Virgo supercluster, we're part of a much larger landscape with many valleys, ridges, and gentle slopes. Galaxies flow gradually along these contours, pulled by massive clusters, yet still influenced by the overall expansion of space. This layered organization reveals something subtle about the universe. Structure exists at multiple scales. Stars gather into galaxies. Galaxies gather into groups. Groups gather into superclusters. Each layer contains the previous one, nested like Russian dolls, each expanding outward in scale by enormous factors. When we first described the Milky Way's width of 100,000 light-years, it felt incomprehensibly vast. Now, within the Virgo supercluster, that galaxy becomes a tiny fraction of a much larger system. The local group, once immense at 10 million light-years across, is only one small region inside this 100 million light-year wide structure. Perspective keeps shifting. From within the Virgo supercluster, the Milky Way is no longer a dominant spiral. It is a modest member of a modest group located in the outskirts of a far larger congregation. And importantly, the Virgo supercluster itself is not the ultimate boundary. For many years, astronomers believed it was one of the largest meaningful structures in our cosmic neighbourhood. But as observational techniques improved and galaxy surveys became more detailed, an even larger organisation emerged, one that would redefine our understanding of our place. But before moving outward again, let us linger briefly at this scale. Imagine rising high above the Virgo supercluster. Below you, clusters glow like islands of light. Between them stretch vast dark regions where galaxies are sparse. Filaments, thin, elongated strands of galaxies, connect one cluster to another, forming a faint lattice across space. The universe, even here, does not appear random. It shows patterns, threads, nodes of brightness, regions of quiet emptiness. And we are somewhere within this immense assembly, orbiting quietly around a typical star in a typical galaxy, in a typical group. located in the outer regions of a supercluster that itself is part of something even larger. There is no central throne here, no spotlight, just scale unfolding in layers. As the view continues to widen, the Virgo supercluster will soon be revealed as only one branch of an even more expansive cosmic structure, a structure so vast that its boundaries stretch hundreds of millions of light-years beyond what we have yet described. Now allow the size of the Virgo supercluster to settle softly in your thoughts. 100 million light-years across, thousands of galaxy groups, countless trillions of stars, and yet still not the end of the hierarchy. The widening continues. For many years, the Virgo supercluster seemed like a grand boundary. It felt like the outer layer of our cosmic neighborhood. But as astronomical surveys became more detailed, something surprising emerged. The Virgo supercluster was not an isolated structure. It was part of something even larger. That larger structure was given a name with a quiet, poetic meaning: Laniakea. In the Hawaiian language, the name means immeasurable heaven, and the name is fitting. Laniakea stretches across roughly 500 million light-years. To say that gently, if light began travelling from one side of the structure at the speed it always moves, about 300,000 kilometres each second, it would take 500 million years to reach the other side. 500 million years ago on Earth, life was only beginning to diversify in the oceans. Forests as we know them did not yet exist. Entire geological eras separate us from that starting point. That is the scale of this structure. Unlike a simple cluster, Laniakea is defined not only by its visible arrangement of galaxies, but by motion. Astronomers carefully measured how thousands of galaxies are moving, not just their recession from cosmic expansion, but their local motions relative to one another. When they mapped these movements, a pattern appeared. Galaxies were not drifting randomly, they were flowing. Like leaves carried by a slow river, galaxy groups across this immense region were drifting toward a shared gravitational basin. That basin lies in a region sometimes referred to as the Great Attractor. The name sounds dramatic, but its meaning is simple. It is an area of higher mass concentration, likely a massive cluster or collection of clusters whose gravity gently pulls surrounding galaxies toward it over immense spans of time. Rather than imagining a single object acting like a magnet, it helps to picture a broad valley in a landscape. If rain falls across a large region of hills, the water will eventually find its way downhill into rivers and then toward a basin. It does not rush all at once. It meanders, guided by the subtle slopes of the terrain. Galaxies in Laniakea behave in a similar way. They drift gradually along invisible contours shaped by mass, flowing toward gravitational low points. The Virgo supercluster, once thought to stand alone, is actually just one ridge within this larger landscape. Our local group in turn is a small tributary within that greater flow. This way of defining structure, by movement rather than simple proximity, is one of the more elegant ideas in modern cosmology. Instead of drawing boundaries based purely on where galaxies sit, astronomers asked a different question. Where are they going? The answer revealed that we are part of a vast river of galaxies slowly drifting together across 500 million light-years of space. And yet even this immense region is not a solid object. Laniakea is not a tightly bound cluster in the way the local group is. The expansion of space still operates across these scales. Gravity influences motion locally, but the larger cosmic stretching continues. It is as if Laniakea is a region of slightly denser currents within an ocean that is steadily widening. Now consider again how perspective shifts. The Milky Way, 100,000 light-years across, once seemed vast beyond measure. The local group, 10 million light-years wide, expanded that measure dramatically. The Virgo supercluster, 100 million light-years across, stretched the imagination further still. And now Laniakea, spanning 500 million light-years, gathers all of those structures into a single flowing system. If the Milky Way were the size of a coin, Laniakea would be something closer to an entire continent. And yet even Laniakea is not the final boundary. When astronomers map the distribution of galaxies on even larger scales, they see that Laniakea itself is just one strand within an even grander pattern. Superclusters connect to other superclusters through long filaments of galaxies. Between them lie enormous voids, vast regions nearly empty of galaxies. The universe on its largest scales resembles a web. But before stepping fully into that web, it is worth pausing with this idea of flow. We're not simply located somewhere in space. We are moving within a larger current. The Earth orbits the Sun. The Sun orbits the Milky Way's centre. The Milky Way drifts within the local group. The local group moves within Laniakea, gradually drawn toward deeper gravitational regions. Motion exists at every scale. And yet all of this motion unfolds slowly enough that the night sky appears still. As you rest there now, the planet beneath you spins, the solar system arcs around the galaxy drifts within its group, and the group participates in a gentle, half-billion light-year wide flow through Laniakea. There is no rush in these movements, no sharp edges, only gradual change measured across hundreds of millions of years. Laniakea, the immeasurable heaven, is a reminder that even what once felt like a boundary can turn out to be a smaller part of something larger, and beyond it lies the structure that truly reshapes our understanding of cosmic scale, the vast interconnected web that spans the observable universe. If we could travel far enough away, far beyond Laniakea, beyond the familiar superclusters, and look back at the universe on its grandest visible scale, we would not see a smooth sea of evenly scattered galaxies. We would see a web, not a delicate spider web stretched between tree branches, but something far larger and more intricate, a three-dimensional network of glowing threads and vast empty spaces extending across billions of light years. This is what astronomers call the cosmic web. Galaxies not spread uniformly through space. Instead, they cluster along enormous filaments, long strands of matter that can stretch for hundreds of millions of light years. At the intersections of these filaments lie dense nodes, where clusters and superclusters gather. Between the threads are vast regions known as voids, immense volumes of space containing very few galaxies at all. If you imagine soap bubbles pressed together in a sink, you might notice that the bubbles meet along thin films and gather at junctions. The cosmic web has a similar appearance. Galaxies trace out the thin surfaces and intersections, while the interior spaces remain comparatively empty. Or picture a lace fabric stretched across the dark. The bright strands are where galaxies reside. The open spaces are the voids. This structure did not form instantly. It emerged, gradually over billions of years, shaped by gravity and the subtle distribution of matter in the early universe. Shortly after the universe began expanding, matter was not perfectly smooth. Tiny variations in density, almost unimaginably small differences, existed from place to place. Over time, gravity amplified these slight irregularities. Regions that were slightly denser attracted more matter. As they grew heavier, they pulled in even more material. Slowly, like snow gathering on the windward side of a hill, these denser regions became the seeds of galaxies and clusters. Dark matter played a crucial role in this process. Although dark matter cannot be seen directly, its gravitational influence is strong. It began clumping together before ordinary matter did, forming invisible scaffolds across space. Ordinary matter, gas that would later form stars, fell into these dark matter wells, igniting the first galaxies. You can imagine dark matter as the hidden framework of a building under construction. The beams are invisible in the final structure, but without them, the walls would never stand. Over billions of years, this framework guided the formation of the cosmic web. Filaments grew denser, clusters formed at intersections, voids expanded as matter flowed away from less dense regions. Today, when astronomers map the positions of millions of galaxies, they see this pattern clearly. The universe resembles a vast network of luminous strands. The scale is difficult to grasp. Some individual filaments stretch across distances greater than 100 million light-years. Entire superclusters are connected along these threads. Voids between them can span hundreds of millions of light-years as well. Within one such void, if you were to stand on a planet orbiting a star in one of the rare galaxies present, your night sky might appear eerily sparse. Instead of seeing neighbouring galaxies as faint smudges, you might see almost nothing beyond your own. The nearest large galaxy could be hundreds of millions of light-years away. The cosmic web contains both immense density and immense emptiness, and we are located along one of its threads. Laniakea is part of a filament within this larger web. Our local group is a tiny region within that filament. The Milky Way is a small spiral galaxy within the local group, and our solar system is a minute detail inside the Milky Way, layer within layer, thread within thread. As we continue widening our perspective, the question grows sharper. How large is the entire observable universe compared to our galaxy? The cosmic web gives us a visual answer. If the Milky Way were a grain of sand, the web would be an entire landscape of dunes stretching beyond the horizon. But there is still another shift to make. All of this, the web, the filaments, the superclusters, exists within what we call the observable universe. That word matters. Observable. Because there is a limit to how far we can see. Light travels at a finite speed, about 300,000 kilometers per second, fast enough to circle Earth multiple times in a single second. But even at that incredible speed, light takes time to cross vast distances. The universe has been expanding for about 13.8 billion years. That means light has only had that amount of time to travel toward us since the earliest moments of cosmic history. As a result, there is a horizon beyond which light has not yet reached us. Everything we see, every filament, every void, every cluster, is contained within a sphere of visibility defined by the travel time of the light. And that sphere, astonishingly, spans about 93 billion light-years in diameter. But before we fully step into that scale, let the cosmic web settle in your mind. A network of galaxies woven across space, dark matter as its hidden framework, voids like silent oceans between glowing strands. We are not floating in a random scatter. We are part of a grand pattern, structured, interconnected, vast beyond intuition. And yet, all of it still fits within a larger boundary defined not by walls, but by light itself. When astronomers first began mapping the positions of large numbers of galaxies, something unexpected emerged. They did not see a random scatter. Instead, they saw pattern. Galaxies appeared strung together along long, delicate strands. These strands stretched across unimaginable distances, sometimes for more than 100 million light-years. At the intersections of these strands, dense clusters gathered like knots in a net, and between them lay immense regions where galaxies were few and far between. This pattern became known as the cosmic web. But what is most fascinating is not simply that the web exists, it is how it came to be. Long before galaxies formed, the universe was filled with a nearly uniform mixture of matter and radiation. But nearly uniform is not perfectly uniform. Tiny variations existed, slight differences in density from one region to another. These differences were almost imperceptible, smaller than 1 part in 100,000. Yet gravity is patient. Where matter was just slightly denser, gravity pulled a little more strongly. Over millions and then billions of years, those slightly denser regions attracted more material. Like snow gathering around a small bump in a field, the bump grew larger as more snow accumulated. Dark matter played the leading role in this process. Though invisible to our eyes and telescopes, dark matter interacts through gravity. It does not emit light, absorb light, or reflect light, but it carries mass, and mass bends the fabric of space. In the early universe, dark matter began to clump first. It formed vast halos and elongated structures long before stars were born. Ordinary matter, hydrogen gas and other elements, fell into these dark matter wells, compressing until the first stars ignited. You might imagine dark matter as the hidden skeleton of the universe. The bones do not shine, but they give shape to everything that does. Over time, these dark matter structures connected, stretching into long filaments. Where multiple filaments intersected, massive clusters formed. Where matter flowed away, large empty spaces emerged. The web was not woven by threads of light. It was shaped by gravity's steady pull, and this web continues to evolve. Galaxies drift slowly along these filaments, pulled toward denser nodes. Clusters grow as they absorb surrounding material. Voids expand as matter flows outward toward the strands. If you could rise high above this structure and watch it unfold over billions of years, you would see something like rivers slowly carving valleys into a landscape. Matter does not rush. It glides, guided by invisible contours. The filaments themselves are not solid bridges. They are regions where galaxies are more concentrated, like beads threaded along invisible strings. Some filaments span distances so large that even light would take hundreds of millions of years to travel from one end to the other. And yet, despite this staggering scale, the web has a surprising delicacy. Imagine lace stretched across the dark, or frost patterns forming on a window in winter. Thin lines branch and reconnect. Nodes thicken at intersections. Wide spaces remain open between them. The universe on its largest visible scale resembles that kind of intricate design, and within one of those strands lies Laniakea. Within Laniakea lies the Virgo region. Within that region lies the local group. Within the local group lies the Milky Way. Within the Milky Way lies our solar system. Layer after layer, each nested inside a structure far larger than the one before. Now pause for a moment and imagine standing in one of the great voids between filaments. Voids can span hundreds of millions of light years. Inside them, galaxies are sparse. The night sky from such a location might look different. The nearest major galaxy could be so far away that it appears almost invisible. Instead of a sky dotted with distant smudges of light, you might see a deeper, darker emptiness. The cosmic web contains both abundance and vast silence, and it is important to understand that this web does not sit inside something like a container. It is not wrapped by walls. It extends throughout the observable universe. The observable universe, the portion we can see, spans about 93 billion light-years across. The cosmic web fills that entire region, stretching in every direction we can observe. Beyond that horizon, we cannot see, not because nothing is there, but because light from those regions has not yet had time to reach us. But within what we can observe, the web is everywhere. The fact that such order arises from simple gravitational attraction is one of the most remarkable features of the cosmos. No designer stitched it thread by thread. No guiding hand arranged galaxies into place. Gravity, acting patiently over billions of years, shaped the universe into this vast network. And yet the result is almost artistic, a tapestry of matter suspended in darkness. As you rest and breathe, the planet beneath you spins quietly within this web. The Milky Way drifts along one of its strands. Entire clusters slowly shift position along invisible gravitational pathways. It all unfolds so gradually that nothing appears to move, and yet everything is in motion. The cosmic web is not merely a background structure. It is the grand architecture within which every galaxy, every star, and every planet exists. And astonishingly, all of it, every filament and void, fits within a sphere of visibility defined by the time light has had to travel since the universe began expanding. The next step in our widening view will be to understand that limit, to explore what it means that we can only see so far, and that seeing far is the same as seeing back in time. But for now, let the image of the web remain. Threads of galaxies stretched across billions of light years, dark matter forming an invisible skeleton, voids like quiet oceans between luminous strands, and somewhere along one of those threads, a small spiral galaxy turning gently in the dark. When we imagine the universe, we often picture brilliance, spirals of stars, clusters glowing like distant lanterns, filaments stretching like luminous threads across darkness. But just as important as what is present is what is absent. Between the strands of the cosmic web lie immense regions known as voids. A void is not absolute emptiness. It is not a perfect vacuum without particles. Rather, it is a region where galaxies are extremely sparse. Compared to the dense filaments and clusters, these areas contain far fewer galaxies per unit volume. Some cosmic voids stretch across distances of 200 million light-years or more. That means if light began travelling from one side of such a void, it would take 200 million years to reach the other. To place that gently in perspective, 200 million years ago on Earth, the continents were arranged differently. Dinosaurs were still walking the planet. The time it would take light to cross a single void is comparable to the span of entire biological eras. And yet within that enormous volume, there may be only a handful of galaxies scattered thinly through space. If you could somehow stand on a planet orbiting a star in one of those rare galaxies inside a void, your night sky would feel different. From Earth, when astronomers point powerful telescopes outward, they see neighbouring galaxies in many directions. Even if faint, even if small, the universe appears populated. But within a deep void, the nearest major galaxy cluster might lie tens or even hundreds of millions of light-years away. It could be so distant that it would appear as a barely detectable smudge of light, even to advanced instruments. The sky might look darker, more isolated. The surrounding cosmic landscape would feel vast and quiet. There is something strangely peaceful in that thought. Cosmic voids are not mistakes in the universe's design. They are natural consequences of gravity's sorting process. As matter flowed toward denser filaments over billions of years, the less dense regions became emptier still. Imagine rain falling across a wide plain. Water gathers into streams and rivers, carving channels as it flows. The land between the rivers dries out, becoming open fields. Voids are those open fields. They occupy most of the volume of the universe. The majority of space, on large scales, is found within these vast, underpopulated regions. And yet, because galaxies are concentrated along filaments, we tend to think of the universe as crowded. In truth, most of it is spacious beyond comprehension. Even the emptiness, however, is not static. Voids expand as the universe expands, as galaxies continue to move along, filaments, and toward clusters. The contrast between dense and sparse regions becomes more pronounced. Over cosmic time, voids grow larger. There is an elegance in this structure. The universe did not spread matter evenly like butter on bread. It allowed gravity to sculpt it into patterns, dense strands woven through immense quiet spaces. The interplay between fullness and emptiness defines the cosmic web, and this balance also shapes perspective. When we ask how large the universe is compared to our galaxy, we often focus on the dense regions, the bright clusters and spirals. But most of the observable universe is not filled with galaxies packed tightly together. Most of it is void. If the Milky Way were a single grain of sand, the empty desert surrounding it would stretch far beyond sight. And yet, that emptiness is not meaningless. It is part of the architecture. In a way, the cosmic web resembles the human brain. Neurons form intricate networks, with synapses connecting nodes. Between them lies space. That space is not wasted. It allows structure and separation. Similarly, the voids give definition to the filaments. Without emptiness, there would be no pattern. Now consider once more our own location. We're not deep inside a vast void. Our galaxy lies along a filament within Laniakea, surrounded by other groups and clusters. We inhabit a relatively average region of the cosmic web, not especially dense, not especially empty. And that average placement once again reinforces a recurring theme. We are not at a special centre. We are not at a rare extreme. We are somewhere typical within an immense structure defined as much by its silences as by its light. As you rest, imagine those vast voids stretching quietly between filaments. Imagine distances so large that light takes hundreds of millions of years to cross them. Imagine skies where neighbouring galaxies are faint whispers rather than glowing companions. The universe is not only a tapestry of brilliance, it is also a landscape of stillness, and together, filaments and voids, it forms the grand structure that fills the observable cosmos. Soon, we will shift our attention from structure to counting, from mapping where galaxies are to asking how many there truly are. But for now, let the idea of cosmic emptiness settle gently. Vast oceans of space, rare islands of light, and a small spiral galaxy resting along one luminous thread. Once we begin to see the universe as a web of filaments and voids, another question naturally arises. How many galaxies are there? At first glance, this sounds like a straightforward counting problem. But the universe does not offer itself up neatly for census taking. For many years, astronomers estimated that the observable universe contained roughly 100 billion galaxies. That number became widely quoted. It appeared in textbooks, documentaries, and classroom lessons. 100 billion. It already felt enormous, but that estimate was based on what telescopes could see at the time. When the Hubble Space Telescope began taking extremely deep images of small patches of sky, something remarkable happened. Astronomers pointed Hubble toward what appeared to be an almost empty region. No bright stars, no obvious galaxies. They let the telescope stare for days. The result was astonishing. That tiny patch of darkness, no larger than a grain of sand held at arm's length against the sky, revealed thousands of galaxies. Not stars within our own galaxy, but entire galaxies far beyond the Milky Way. Each faint smudge in the image was a city of stars. If such a small patch of sky contained thousands of galaxies, what might the entire sky contain? By carefully extrapolating from these deep-field images, astronomers began refining their estimates. As techniques improved and fainter galaxies were detected, the number increased. Eventually, some studies suggested that the observable universe might contain not merely 100 billion galaxies, but perhaps 2 trillion. 2 trillion, that is 2,000 billion. The revision did not mean that new galaxies had suddenly formed. It meant that we had previously been unable to see the faintest and most distant ones. Imagine standing on a hill overlooking a city at night. At first, You might count only the brightest lights, the skyscrapers, the stadiums, the highways. But as your eyes adjust, smaller lights appear. Windows, street lamps, porch lights. The longer you look, the more you notice. The universe is similar. The deeper we look, the more galaxies emerge from the darkness, and this story is still unfolding. The James Webb Space Telescope, launched decades after Hubble, is capable of seeing even farther and fainter. It observes in infrared light, which allows it to detect galaxies whose light has been stretched by cosmic expansion over billions of years. In its earliest deep images, Webb revealed galaxies that appear surprisingly numerous in the early universe. Some astronomers were startled by how many faint systems showed up so quickly in cosmic history. This does not mean our previous models were wrong in a dramatic sense. It means the picture is still being refined. We are still counting, and here is something important to remember. The number 2 trillion refers only to the observable universe, the portion of the cosmos from which light has had time to reach us since the beginning of expansion. Beyond that horizon, there may be more galaxies, perhaps many more, we do not know. This uncertainty is not a weakness of science, it is part of its strength. Science does not claim final answers, it measures, revises, refines. When we compare the Milky Way to the observable universe, we are not comparing it to a perfectly mapped and completed territory. We are comparing it to a vast region that is still being charted. But even with uncertainty, the scale is staggering. If there are 2 trillion galaxies in the observable universe, and if the Milky Way contains somewhere between 100 billion and 400 billion stars, then the total number of stars across all galaxies becomes almost incomprehensible. There may be more stars in the observable universe than grains of sand on all the beaches of Earth. That comparison is often used, and while it is poetic, it is also grounded in serious estimation. And yet even these comparisons are approximations. Some galaxies are large and bright, others are tiny and faint. Some formed early in cosmic history, others formed later. Some are actively forming new stars, others have grown quiet. The census is ongoing. What matters for our question is this. The Milky Way is one galaxy among perhaps 2 trillion in the observable universe, not 1 in 1,000, not 1 in 1,000,000, 1 in trillions. And yet this does not make our galaxy insignificant, it simply places it within context. When you look at the night sky, the stars you see belong to our galaxy alone. The faint smudges beyond are neighbouring galaxies within the local group or nearby clusters, but the overwhelming majority of galaxies in the observable universe are far too distant to be seen without powerful telescopes. Most galaxies exist beyond the reach of our unaided eyes. As we prepare to widen our view further, one final shift awaits. Distance in the universe is not just about space, it is about time. When we look at a galaxy 1 million light-years away, we see it as it was 1 million years ago. When we look at galaxies billions of light-years away, we see them as they were billions of years in the past. Telescopes do not merely count galaxies, they look backward through history. And that realization brings us to one of the most profound aspects of cosmic scale. The idea that seeing far is the same as seeing back. But for now, let the number settle gently. Perhaps 2 trillion galaxies within the observable universe, each with billions of stars, and among them one spiral galaxy turning quietly in a filament of the cosmic web. When you look up at the night sky, it feels immediate. The stars seem present, close, as if they exist in the same moment as you. But the universe does not work that way. Light takes time to travel. Even though light moves at about 300,000 kilometers per second, fast enough to circle the Earth several times in a single second, it is not instantaneous. Distance and time are quietly linked by the motion of light. When sunlight reaches Earth, it has travelled for about 8 minutes. You're not seeing the sun as it is right now, you're seeing it as it was 8 minutes ago. That delay is small enough to feel negligible. But as distances increase, so does the delay. If a star lies 100 light years away, its light takes 100 years to reach us. The star you see tonight shines from the past. Its image began travelling toward you before most modern technologies existed, and when we look beyond our galaxy, the time shift becomes vast. The Andromeda galaxy is about 2.5 million light years away. That means when you see Andromeda through a telescope, you are seeing it as it was 2.5 million years ago. At that time, early human ancestors were just beginning to walk upright on Earth. Distance becomes history. A galaxy 10 million light years away appears as it was 10 million years ago. A galaxy 1 billion light years away appears as it was 1 billion years ago. Light is not just illumination. It is a messenger carrying ancient information. This is why telescopes are sometimes described as time machines. They do not travel through time physically, but they allow us to observe different eras of cosmic history simply by looking farther away. When astronomers point powerful telescopes toward extremely distant galaxies, they are peering into the early universe, back toward a time when galaxies were younger, smaller, and still forming their first generations of stars. And there's another subtle effect at work. As the universe expands, space itself stretches. When light travels across billions of light years of expanding space, its wavelength stretches as well. Blue light can shift toward red. Visible light can shift into infrared. This phenomenon is known as redshift. But rather than thinking of it as a technical term, it helps to imagine sound. If you hear a train whistle as it moves away from you, the pitch lowers. The sound waves stretch slightly as the source recedes. Light behaves in a similar way. As galaxies move away due to cosmic expansion, the light they emit is stretched to longer wavelengths by the expanding space it crosses. The farther a galaxy is, the more its light is stretched. This stretching allows astronomers to estimate how far away galaxies are, and therefore how far back in time we're seeing them. When telescopes like the James Webb Space Telescope detect extremely redshifted galaxies, they are observing light that began its journey more than 13 billion years ago, shortly after the universe itself began expanding. In other words, we can see galaxies forming not long after the first stars ignited. And yet, even as we look back so far, there is a limit. The universe is about 13.8 billion years old. That number represents the time since the beginning of cosmic expansion. You might expect that the observable universe would therefore extend 13.8 billion light years in every direction. But because space has been expanding while light travelled, the actual observable radius is larger. The diameter of the observable universe is about 93 billion light years. This number can feel puzzling at first, but it simply reflects the fact that the universe has been stretching while light was on its way to us. The key idea is this: seeing far means seeing old. The night sky is not a snapshot of the present universe, it is a layered archive. Nearby, stars appear almost current. Distant galaxies appear ancient. Every direction you look is also a look into history, and this realization reshapes our sense of scale. When we say there may be 2 trillion galaxies in the observable universe, we are not describing a single moment frozen in time. We are describing a vast collection of different moments, some galaxies as they were billions of years ago, others closer to our present. The cosmic web you imagine is not static. It is a tapestry woven across time. As you rest, imagine light leaving a distant galaxy billions of years ago. Imagine it travelling steadily across expanding space, passing through filaments and voids, crossing hundreds of millions of light years, until finally, tonight, it enters a telescope on Earth. That faint signal began its journey long before our species existed, and now it reaches you. Distance is time, and the farther we look, the deeper into cosmic history we see. This understanding prepares us for the next, widening of perspective, an explanation of why the observable universe is larger than the simple age of the cosmos might suggest. But for now, allow the idea to settle gently. The sky above you is not only wide, it is ancient. At first, something about the universe seems puzzling. If the universe began expanding about 13.8 billion years ago, you might expect that the farthest light we could possibly see would have travelled for 13.8 billion years. That part is true. But then comes the surprise. The observable universe, the region from which light has had time to reach us, is not 13.8 billion light-year across. It is about 93 billion light-years in diameter. How can that be? The answer lies in something subtle and beautiful. Space itself expands. To understand this, imagine a loaf of dough resting on a kitchen counter. Mixed into the dough are small raisins scattered throughout. Now imagine placing that dough into an oven. As it bakes, the dough rises, it stretches in every direction. The raisins do not actively move through the dough. Instead, the dough between them expands. From the perspective of any single raisin, all the other raisins appear to move away. The farther a raisin is, the faster it appears to recede, because there is more expanding dough between them. This is similar to how the universe behaves. Galaxies are not flying outward through empty space from a central explosion. Instead, space itself is stretching. The distances between galaxies grow because the fabric of space expands. Now imagine a raisin near the centre of the loaf, watching another raisin some distance away. As the dough rises, the light travelling between them must cross expanding dough. While the light is on its journey, the dough continues to stretch. So even though the light may have been travelling for 13.8 billion years, the total distance between the raisins by the time the light arrives is greater than 13.8 billion light years. The space expanded while the light was in transit. This is why the observable universe today measures about 93 billion light years across. The light we see from the most distant regions began travelling when the universe was very young. But during its long journey, the universe continued to expand. It is not that anything moved faster than light through space, rather space itself expanded. That distinction is important. The speed of light, about 300,000 kilometers per second, remains the fastest speed at which information can travel through space. But space itself is not bound by that limit in the same way. Over vast distances, the expansion of space can cause galaxies to recede from one another at speeds that, when calculated simply as distance divided by time, exceed the speed of light. This does not violate the laws of physics. It reflects the stretching of space, not motion through space. Returning to the dough analogy, imagine two raisins placed very far apart in the loaf. As the dough rises, the space between them increases more quickly than between raisins placed closer together. In the universe, the farther away a galaxy is, the faster it appears to move away from us due to expansion. And importantly, every galaxy sees this same pattern. From the perspective of any observer anywhere in the universe, distant galaxies recede in all directions. There is no central raisin. The expansion happens everywhere at once. Now bring this back to our comparison. The Milky Way spans about 100,000 light-years. The observable universe spans about 93 billion light-years in diameter. That difference in scale is immense, but it is not simply a matter of static size, it is a matter of dynamic history. The observable universe is a snapshot of how far light has travelled through a constantly stretching fabric. If the universe had not expanded, the observable radius would match the age of the universe more closely. But because expansion has been occurring the entire time, distances have grown while light was travelling, and this expansion continues even now. Galaxies not gravitationally bound to us drift farther away over time. In the far future, billions of years from now, distant galaxies will recede so far that their light will no longer be able to reach us. The observable universe will shrink in practical terms, even though space itself continues expanding. This is not a dramatic catastrophe. It is a gradual unfolding. As you sit quietly, the space between galaxies is increasing. The Milky Way and Andromeda are moving toward each other, because gravity binds them locally. But distant galaxy clusters are drifting farther away. Expansion operates on the larger scales. It is a soft, steady stretching. So when we say the observable universe measures about 93 billion light-years across, we are describing the current scale of a region shaped by billions of years of expansion. We are describing a sphere of visibility defined by light's journey through expanding space, and within that vast sphere lies the cosmic web, the filaments and voids, the superclusters and groups, the Milky Way, and finally our small solar system. The puzzle dissolves when we realize that the universe is not static. It is not a fixed container. It is an evolving fabric, stretching gently over time, and that gentle stretching explains why the universe appears larger than its age alone might suggest. The next question that arises naturally is this: is the observable universe the whole universe, or is it merely the portion we can see? But before stepping into that mystery, let the image of rising dough settle softly in your mind. Space expanding, distances growing, light travelling faithfully through a universe that never stands still. When we speak of the observable universe, we are speaking of a boundary defined not by walls, but by light. There is no glowing edge marking where the universe stops. There is no cliff beyond which existence ends. Instead, there is a horizon, an invisible limit set by time and the speed at which light travels. Light moves swiftly, about 300,000 kilometers every second. But even at that astonishing speed, it requires time to cross great distances. And because the universe has been expanding for about 13.8 billion years, light has only had that much time to travel since the beginning of cosmic expansion. The observable universe is the region from which light has had enough time to reach us. If a galaxy lies so far away that its light has not yet arrived, we cannot see it, not because it is hidden behind something, but because its signal is still on the way. This horizon is not centered on Earth in a special sense. Every observer anywhere in the universe has their own observable sphere, defined by the same principle. From their perspective, they are at the center of what they can see. From ours, we're at the center of our visible region. But this does not imply that we occupy a privileged position. It is simply how horizons work. If you stand in the middle of a vast desert, the horizon appears as a circle around you. No matter where you walk, you remain at the center of your visible region. The horizon moves with you. In the same way, the observable universe moves with any observer. Now consider what lies beyond that horizon. We do not know. The laws of physics, as far as we understand them, suggest that the universe beyond the observable region is likely similar in structure to what we see within it. There is no reason to believe that galaxies suddenly cease to exist beyond the limit of our visibility. But we cannot confirm that directly. There may be more filaments, more voids, more superclusters stretching beyond our cosmic horizon. The universe may extend vastly farther than the 93 billion light-years we Satya can observe. It may even be infinite in extent. Infinite does not mean boundless chaos. It simply means that space might continue without edge in all directions. Yet here, caution is important. Science does not claim certainty about what lies beyond observation. It models possibilities based on known physics and measured expansion. It examines patterns in the cosmic microwave background radiation, the faint afterglow of the early universe, to estimate curvature and geometry. Those measurements suggest that space is remarkably flat on large scales. A flat geometry implies that the universe could be infinite, or at least so large that its curvature is imperceptible within our observable region. But infinite is a delicate word. It is not a dramatic proclamation. It is a quiet mathematical possibility. For now, what we can say with confidence is this: the observable universe is finite. It has a measurable diameter of about 93 billion light-years. Within that region lie perhaps 2 trillion galaxies woven into a vast cosmic web. Beyond that, we do not yet see. The horizon is not an ending, it is a limit to our knowledge, and there is something deeply human about that. Throughout history, horizons have always invited curiosity. Sailors once looked toward the line where ocean met sky and wondered what lay beyond. Astronomers now look toward the cosmic microwave background, the earliest light we can detect, and wonder what preceded it. The edge we cannot see is not a barrier meant to frustrate us. It is a reminder that knowledge unfolds gradually. If the universe is larger than what we observe, it simply means that light from those regions has not yet had time to arrive. In the distant future, if cosmic expansion allows, some currently unseen regions might eventually come into view, or they may recede forever beyond reach. Expansion complicates this picture. As space stretches, some distant galaxies move away so quickly that their light will never reach us, even given infinite time. They cross what is known as the cosmic event horizon. Beyond that boundary, events can occur, but their light will never arrive here. Again, this is not a wall. It is a consequence of expansion. The universe does not hide its edges. It simply expands faster than light can traverse certain distances. So when we ask how large the universe is compared to our galaxy, we must remember this distinction. The Milky Way is about 100,000 light-years across. The observable universe spans about 93 billion light-years. The entire universe may extend far beyond that. Our galaxy sits within a filament of the cosmic web, inside Laniakea, inside a supercluster, inside a web that fills the observable region. And beyond that region, space may continue silently, filled with galaxies we will never see. There is something peaceful in this realization. The universe is not confined to what we can measure. Our vision is limited, but reality may be far broader. As you rest, imagine standing at a cosmic shoreline, not at the end of existence, but at the edge of visibility. Beyond the horizon lies more ocean, stretching into darkness, perhaps without limit. We cannot see it, but its possibility hums quietly in the background of cosmology. And within the sphere we can observe, we already find scale so vast that our galaxy becomes a delicate spiral within an immeasurable sea. After travelling outward through galaxies, groups, superclusters, filaments, voids, and the observable horizon, we can finally return to the original question. How large is the universe compared to the Milky Way? The Milky Way stretches about 100,000 light-years across. The observable universe stretches about 93 billion light-years across. Those numbers alone are difficult to feel. So instead of holding them as abstract figures, let us translate them into something more tangible. Imagine the Milky Way as a small coin, resting on your palm. Not a large dinner plate, not a city block, just a coin. Now imagine the observable universe scaled proportionally. It would not be another coin, not even a large field. It would stretch across something closer to the size of a continent. The difference is not modest. It is not subtle. It is vast beyond instinct. If the Milky Way were reduced to the width of a human hair, the observable universe would extend for many kilometers. If our galaxy were the size of a single grain of sand, the observable universe would resemble an entire desert. And yet, remember, this is only the observable universe, the portion we can see. Within that immense sphere lie perhaps 2 trillion galaxies. Each galaxy may contain billions or hundreds of billions of stars, and within one of those stars' planetary systems, on a small rocky world orbiting an average star, you are resting quietly. It is easy, when hearing such comparisons, to feel diminished, but scale alone does not determine meaning. When we say the Milky Way is one among 2 trillion galaxies, we are describing number, not value. We are describing distribution, not significance. Still, the scale is worth appreciating. The Milky Way feels immense when we consider that light takes 100,000 years to cross it. That number alone stretches imagination. Civilizations rise and fall within a few thousand years. The entire span of recorded human history covers only a tiny fraction of that distance in light travel time. Yet compared to the observable universe, our galaxy is a small structure embedded within something almost unimaginably larger. It is similar to standing inside a forest and examining a single tree. That tree may be tall, strong, and complex. It may host birds, insects, moss, and entire ecosystems on its bark. But when you step back and see the entire forest stretch into the horizon, the tree becomes one element within a broader landscape. The Milky Way is such a tree. The observable universe is the forest. But even that analogy is incomplete, because the forest in this case spans 93 billion light-years. The ratio between 100,000 and 93 billion is so large that stating it numerically risks turning it into abstraction again. So let us instead hold the feeling of contrast. A galaxy is vast beyond comprehension when considered alone. The universe makes galaxies feel small, and yet this pattern repeats at every scale. The solar system once felt large when compared to Earth. The Milky Way made the solar system feel small. The local group made the Milky Way feel smaller. The Virgo region made the local group feel modest. Laniakea made Virgo feel like a branch. The cosmic web made Laniakea feel like a thread. And the observable universe holds all of it within a single sphere of visibility. Each widening step reframes what came before. But here is something quietly remarkable. Even though the Milky Way is small compared to the observable universe, it is not lost within it. Gravity binds it into a filament. The filament connects to clusters. Clusters form part of superclusters. Structure connects everything. We are not isolated fragments drifting randomly. We are embedded within an interconnected web. The comparison between the Milky Way and the universe is not a comparison between something meaningful and something meaningless. It is a comparison between layers of scale. And scale does not erase detail. Within the Milky Way there are star-forming regions glowing with new light. There are ancient stars orbiting the galactic center. There are black holes, nebulae, planetary systems, and perhaps countless other worlds. The fact that this entire galaxy is small relative to the observable universe does not reduce its richness. It simply places it within context. When we look up at the night sky, the stars we see belong almost entirely to the Milky Way. The faint glow of Andromeda represents just one neighbouring galaxy among perhaps 2 trillion. Most of the universe lies far beyond what our eyes can detect. And yet the scale difference, though immense, is not meant to intimidate. It is meant to inform. The Milky Way is not the centre of everything. It's not the largest structure. It is one spiral galaxy among many, resting along a luminous thread in a vast cosmic web that fills a sphere 93 billion light-years across. That is the comparison. A coin and a continent, a tree and a forest, a grain of sand and a desert, and yet within that grain of sand awareness arises. We will turn gently toward that awareness soon, but before doing so, let the scale rest quietly in your thoughts. 100,000 light-years, 93 billion light-years, a galaxy within a universe, small in size, yet fully part of the whole. When we compare the Milky Way to the observable universe, another quiet question arises. If the universe is so vast, where is its centre? It natural to imagine that something so large must have a middle, a throne room of space perhaps, from which everything expanded outward. But modern cosmology suggests something far more subtle. On the largest scales, the universe does not appear to have a central location. This idea can feel counterintuitive at first. After all, when something expands, like a ripple in water, we expect there to be a point from which it began. Yet the expansion of the universe is not like a ripple spreading across a surface. It is not matter moving outward into empty space from a central explosion. It is space itself stretching everywhere at once. To picture this gently, imagine a vast, endless grid drawn across a sheet. Now imagine that every square in that grid slowly increases in size at the same steady rate. The lines between points grow longer, the entire pattern expands uniformly. If you were standing at any one intersection of that grid, you would see all other intersections moving away from you. The farther away a point was, the faster it would appear to recede, simply because there is more expanding space between you. But from that point's perspective, the same thing would be true. It would see all other points receding from it. No point would occupy a special position. Expansion would look the same from everywhere. This is what we observe in the real universe. When astronomers measure distant galaxies, they find that, on average, galaxies recede in all directions. The pattern does not suggest that we are at a centre, it suggests that expansion is uniform. Every galaxy, no matter where it resides, would see the same large-scale pattern. It is as if the universe has no throne room, no elevated platform from which space unfolds. Instead, expansion is woven into the fabric of reality itself. There is also no visible edge. When we speak of the observable universe, we refer to a horizon defined by light's travel time. But that horizon is not a boundary in space, it is a boundary in visibility. If the universe extends beyond what we can see, and current evidence suggests it likely does, then there is no sharp wall marking its end. Even within the observable region, there's no indication that we are near a physical boundary. Galaxies continue in every direction, until we reach the limit imposed by time and light. This lack of centre can feel disorienting at first. Human intuition is shaped by everyday experience. We are used to rooms with walls, cities with centres, objects with edges. But the universe on its larger scales does not follow those familiar patterns. Instead, it resembles something more abstract, an endless expanse where structure exists locally, but no global focal point dominates. This does not mean the universe is chaotic. It is structured, as we have seen in the cosmic web. It is governed by physical laws that apply everywhere we can measure. But it does not revolve around a central stage, and importantly, this does not diminish our location. If there is no centre, then no place is privileged. If there is no edge, then no region is marginal. Every galaxy sits within the expanding fabric equally. In fact, the idea that every observer sees themselves at the centre of their observable universe is a profound symmetry. It means that the laws of physics apply universally. It means that no vantage point is cosmically favoured. You could imagine observers in a distant galaxy, billions of light years away, asking the same question we ask. How large is the universe compared to our galaxy? From their perspective, their galaxy would seem central within their observable horizon, and they too would discover that there is no cosmic throne, no master coordinate, just expansion unfolding everywhere. As you rest and breathe, consider this quietly. The Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way drifts within the local group. The local group flows within Laniakea. Laniakea traces a filament in the cosmic web, and the web itself expands without a central anchor. There is no single spotlight shining on one galaxy, no grand balcony overlooking the whole. Instead, reality is shared evenly across immense scales. The absence of a center is not a statement about insignificance. It is a statement about universality. The same physics that shapes distant galaxies shapes ours. The same expansion that carries faraway clusters outward carries us along. In a universe without a throne, every location is simply part of the whole, and in that shared participation, there is a quiet kind of belonging. Soon, we will turn toward a final reflection, one that considers how small we are in scale, yet how extraordinary it is that we can contemplate the whole at all. But for now, let the idea settle gently. No center, no edge, just an expanding fabric of space in which every galaxy participates equally. We have travelled far, from the familiar curve of the Milky Way spiral, arms to the local group, from superclusters to Laniakea, from luminous filaments to immense voids, from counting galaxies to the expanding horizon of the observable universe. And now, after widening our view to 93 billion light-years across, we arrive at a quiet question. What does this scale mean for us? The Milky Way spans about 100,000 light-years. The observable universe spans about 93 billion light-years. Our solar system is a tiny region within the Milky Way. Earth is a small planet orbiting an average star. Each of us occupies a brief moment in time on that small world. In terms of size alone, we are almost inconceivably small. If the Milky Way were a continent, Earth would be a single grain of sand. If the observable universe were an ocean, our entire galaxy would be a small island within it. And yet something unusual happens here. Within this small region of a small planet in a modest galaxy, matter has arranged itself in such a way that it can reflect upon the whole. The atoms in your body were forged in ancient stars. Hydrogen formed in the earliest moments of cosmic history. Heavier elements were created in stellar furnaces and supernova explosions long before the sun existed. Those atoms now participate in a network of neurons in your brain. Electrical signals travel along pathways built from carbon and oxygen and iron, elements born in distant stars. And somehow, that arrangement gives rise to awareness. Awareness capable of asking how large the universe is. Awareness capable of understanding light travel time and cosmic expansion. Awareness capable of imagining 93 billion light-years. This does not make us large in scale, but it makes us unusual in capacity. The universe, as far as we can tell, is mostly composed of silent matter. Galaxies drift, stars burn, planets orbit. Vast voids stretch in quiet emptiness. Conscious reflection may be rare. We do not yet know how common life is. We do not know how many worlds host beings who can contemplate the cosmic web. Perhaps there are many, perhaps there are few. But here, at least in one small spiral galaxy, in one thin filament of the cosmic web, awareness exists. That fact does not cancel our smallness. It reframes it. Smallness in size does not equal smallness in significance. A single neuron in a human brain is tiny compared to the body. Yet without neurons, awareness would not arise. A single note in a symphony occupies little space, yet without notes, there would be no music. Similarly, Earth occupies little cosmic space. The Milky Way occupies little cosmic volume compared to the observable universe. Yet within that small volume, a remarkable phenomenon has emerged: the ability to know. When we say the Milky Way is one galaxy among perhaps 2 trillion, we are speaking of quantity. When we say the observable universe spans 93 billion light-years, we are speaking of scale. But when we speak of awareness, we are speaking of something different entirely. Scale measures distance. Awareness measures experience. The universe does not seem to revolve around us. It has no central throne. It stretches outward in all directions without preference. And yet, within it, there are places where the universe becomes aware of itself. Through telescopes, it observes its own galaxies. Through equations, it describes its own expansion. Through quiet reflection, it contemplates its own immensity. You're not separate from the cosmos observing it from the outside. You're part of the cosmos observing itself from within. The Milky Way is small compared to the observable universe. You're small compared to the Milky Way, but the chain does not end there. Within you is the capacity to imagine 93 billion light-years, to picture filaments stretching across hundreds of millions of light-years, to understand that light arriving tonight began travelling billions of years ago. There is something deeply gentle about that. We are not at the centre. We are not the largest structure. We are not cosmically privileged. But we are participants. Participants in an unfolding story that began about 13.8 billion years ago and continues to expand even now. As you rest, imagine the cosmic web stretching quietly through space. Imagine galaxies drifting along luminous strands. Imagine the observable horizon glowing faintly at the edge of visibility. And within that vastness, imagine a small spiral galaxy. Within that galaxy, a small planetary system. Within that system, a small world turning slowly. And on that world, awareness. Not grand in size, not central in position, but present. Small in scale, vast in awareness.